Welcome everyone to Young Researchers Colloquium. Our speaker today is Ignacio Vergara, a former PhD of IMPAM, currently employed by the Euler International Mathematical Institution. Ignacio will tell us all about the Haagerup property and its generalizations. Please, the floor is yours.
Thank you, Jacek, for the invitation. I will not tell you all about the Haagerup property and generalizations. I'm just gonna tell a few things. So yeah, the Haagerup property is it's an analytic property of groups which has many different formulations. And the one that we are going to focus on here is isometric actions on Hilbert spaces, and some of its generalizations to other kinds of actions, like actions on LP or affine actions which are not isometric. So I will try to give all the details and definitions. When I don't give details, I'm gonna wave my hands to make it look that I'm giving details, but hopefully everything will be clear. So does this work? No, it doesn't work. Yes.
Now it works.
Okay, so this is the plan. I'm going to introduce the Haagerup property and give some examples. Then I'm going to focus on one particular class of groups, which is lattices in SPN1. So this class of groups is very interesting because it allows us to illustrate several different properties which are related to the Haagerup property and which in some sense give us a motivation for the different generalizations that we will consider. Then I'm going to focus on actions with a uniformly bounded linear part. So those are not isometric actions anymore. And then I'm going to make another jump and consider actions now on subspaces of L1 spaces. Okay, so the Haagerup property. So the setting here, I will consider only countable groups and H Hilbert space, a real Hilbert space. And I would consider isometric actions of this group on H. So this is nothing but a group homomorphism from gamma to the group of isometries of H. And this could be any isometry, but there's a very nice theorem by Mazura and Ulam that says that actually, if we have a surjective isometry between normed spaces, then it must be affine. So that means that there is a linear part and a translation. So actually, what this tells us for actions is that an isometric action of a group on a Hilbert space will be given by affine maps. So it will be given by, if our action is sigma, it will be given by a linear part, which is an isometric representation of the group, and a translation, right? And the fact that this sigma is an action, it implies that this translation B of S has to satisfy this identity, which we call the cocycle identity. And so this translation has to be a So talking about isometric actions, it's talking about isometric affine actions on Hilbert spaces. And this will be the main object that we will look at. So the definition of the Haagerup property is that there exists an isometric action on a Hilbert space, which is proper. So proper means, I put the definition here, when S tends to infinity, then sigma S of X, the norm of it tends to infinity, and that's for every X in H, right? But we can observe that since such actions are given by a linear part and a cocycle, then saying that the action is proper is the same as saying that the cocycle is proper, because this linear part here, I, is it's isometric and therefore bounded, right? So that's why when we talk about the Haagerup property, we talk about proper cocycles for isometric representations. And I put a little sentence here. So I just wanted to say that although this is a very nice definition by itself, it is also very important, and it's a property that has many applications in different areas of mathematics, and I can study of Neumann algebras or the bound cone conjecture, and it has many more. I'm not going to focus on any of that. I just wanted to say that this property is very important. So obviously finite groups, because every action of a finite group is proper. More generally, amenable groups. We have there all the abelian groups and groups with sub-exponential growth and many more examples. Groups which actually was this was the example studied by Haagerup in his famous paper, and that's why we call this property Haagerup property. And more generally, groups acting properly on trees, for which the proof is essentially the same. And there are many more examples. I'm not going to talk much about that. I just wanted to say that since we have this example of trees, there is a class of groups which in some sense generalizes trees or groups acting on trees, which is hyperbolic groups. So hyperbolic groups are essentially groups for which their Cayley graph is hyperbolic. And what does it mean for a graph to be hyperbolic? Well, I'm not going to give the definitions. Over here is where I wave my hands. This is essentially saying that every finite subset of the graph can be approximated by a tree in a certain sense. So what I want to emphasize is that hyperbolic groups are a generalization of free groups, or a generalization of groups acting on trees. So that's why it makes sense to ask the question which I put here: do hyperbolic groups have the Haagerup property? And the answer to this question, we know what it is. It's some hyperbolic groups have the Haagerup property, like the free groups, and some of them don't, which is, for example, lattices in SPN1. So this is the point where, as I said before, we're going to focus on these lattices in SPN1 and see that that they don't have the Haagerup property, but they admit some weaker forms of it. So that will be our motivation for generalizing. So I'm going to define these things. So we take H, the field, skew field, non-commutative field. I don't know. It has many names, division rings, but the quaternions, which is a generalization of the complex numbers. And we take on the vector space H n plus 1 the quadratic form given by the usual scalar product that we like so much, but with a minus sign on the first coordinate. And having a quadratic form, we can look at those matrices, so those linear operators on this vector space that preserve this quadratic form. And actually that is a group, and it has a structure of Lie group, and that's the group that we call SPN1 for every n. So this a Lie group, so it's huge. It's not countable, and I'm focusing only on countable groups. So what we're going to look at is actually lattices in SPN1. So what is a lattice? It's a discrete subgroup such that the quotient has a G invariant probability measure. So it's the generalization to what Zn is to Rn, right? It's a lattice. So for those lattices, what happens to those lattices? There is a very nice theorem that those lattices have property T. What's property T? Like the Haagerup property has many different formulations, but we're going to use this one, which says that every isometric affine action on a Hilbert space has a fixed point. So it's a very strong negation of the Haagerup property. So in particular, lattices in SPN1 do not have the Haagerup property. So we have our first example of groups without the Haagerup property, but these groups satisfy many more properties, which we're gonna look at. So as I said, a hyperbolic group is a group such that its Cayley graph is hyperbolic. And one example of that is co-compact lattices in SPN1. So a co-compact lattice is a lattice that, in addition, the quotient is compact. So those are hyperbolic, and by this theorem of Constant, they don't have the Haagerup property, right? But we have this very nice theorem that says that okay, maybe there are hyperbolic groups that don't have the Haagerup property, but actually for every hyperbolic group we can choose P large enough so that this group has a proper isometric affine action on LP. So this is somehow a weaker form of the Haagerup property that is satisfied by every hyperbolic group, in particular by lattices in SPN1. And I said this is a weaker form. That is really the case, because this property is implied by the Haagerup property. So we have this if a group has the Haagerup property, then it has a proper isometric affine action on an LP space for every P, even P between 0 and 1, for which those are strange spaces, right? So this is a weaker form of the Haagerup property, which is satisfied by all hyperbolic groups. But
may I ask a question, Ignacio? So how is it now? So do we already know that this set of P's for which you have a proper isometric action, do we know it's an interval?
Yes, yes, that was proved quite recently by
Exactly, right? So it's
De La Salle and Maracci. Yes. So yeah.
okay.
What was I saying? Oh, yes. So we can also ask, are there groups that don't have this property, this weaker form of the Haagerup property? And actually there are. So I'm going to focus on this particular example, which is very nice. SLNZ, the n by n matrices over Z with determinant 1. And for those, and for every P, every isometric action of SLNZ for n bigger or equal to 3, an action on an LP space has a fixed point. So I'm stating this theorem only for SLNZ because it's a nice example, but actually this result is far more general and it includes many more higher rank lattices. So this property is a weaker form of the Haagerup property, but it's also a non-trivial property, right? So it's still something very, very interesting. So I'm gonna end the part of actions on LP with that. And now I'm going to focus on a different kind of generalization of the Haagerup property. So we said that an isometric action was given by this linear part, which is an isometric representation, and this cocycle. And what does it mean in terms of the operators pi s that this is an isometric representation? It means that the norm of pi s is 1 for every s in the group. So we can generalize these affine actions, isometric affine actions, by requiring this representation to be maybe not isometric, but uniformly bounded. So we say that it is uniformly bounded if now this supremum is finite, right? So in particular, every isometric representation is uniformly bounded. And now we can ask, okay, we have uniformly bounded representations. We can also consider cocycles for those representations. And so we can define another form of the Haagerup property, but now with uniformly bounded representations. Can we obtain something different defining it that way? And actually, it is the case, and we're going back to our main example of lattices in SPN1. So it was proven that those lattices admit a proper affine action on a Hilbert space with a uniformly bounded linear part. So we know that those groups don't have the Haagerup property. So restricting to isometric representations, this is not true. But if we take this weaker form, then actually they have actions. So again, this opens a new world in some sense, because the behavior can be quite different now if we allow these representations to be only uniformly bounded. Okay, so let me see. Oh, yes. So there's an open problem. I think this question is attributed to whether can we extend this result to all hyperbolic groups? So it makes we had the other theorem for actions in LP for all hyperbolic groups, and now we have this theorem for lattices in SPN1. So it is true for all hyperbolic groups, but this problem like this, it's still open. We don't know, but change the question a little bit. And if we modify this question, we can say some things. And we're going to focus on actions on subspaces of L1. But for this, I first need to introduce another characterization of the Haagerup property, which will allow us to see why this this new definition with actions on L1 is really a generalization. So I'm going back to this theorem that if a group has the Haagerup property, then it has a proper isometric affine action on an LP space for every P. But this has a second part now, which is that now if we assume that gamma has a proper isometric affine action now on a subset of an LP space, and we're going to restrict P to the interval 0, 2, then this group has the Haagerup property. So actually we can combine those two and focus on one single value of P between 0 and 2. I'm going to choose P equal 1 because for that value of P I can say some things, and we have this corollary that a group has the Haagerup property now if and only if it has a proper isometric affine action on a subspace of an L1 space. So here's the connection between Haagerup property and these subspaces of L1. And since we have this characterization, now we can, like we did before, we can generalize it. And of course, what's the generalization? We're going to consider proper affine actions on subspaces of L1, but now with uniformly bounded linear part. So no actions which are not isometric anymore. And for those kind of actions, we actually can say some things for hyperbolic groups. So I'm gonna give a list now of groups for which I can say some things, and then I'm gonna take the result. So we have three classes of groups. So residually finite hyperbolic groups. So I already defined hyperbolic groups, or I waved my hands. And we're going to add this condition of being residually finite, which means that there is a sequence of finite index normal subgroups converging to the trivial group, right? So this being residually finite, and actually it is an open problem in geometric group theory of whether all hyperbolic groups are residually finite. So maybe this could be the class of all hyperbolic groups. We don't know. We're going to look at another class of groups, which is mapping class groups. So if you take a compact surface, so compact orientable surface, so think about a donut or another surface with more holes, with bigger genus. We allow them also to have a finite number of holes, I mean of punctures. And for those classes of surfaces, we can consider the group of orientation preserving diffeomorphisms. So that's a very, very big group, the diffeomorphisms of a surface. But there is a nice normal subgroup, which is the connected component of the identity. So that's all the diffeomorphisms that are isotopic to the identity. And if we mod out by that by that subgroup, we actually obtain a countable subgroup, countable discrete subgroup, which we call the mapping class group of the surface, which we denote sometimes by MCG of sigma, sometimes by mod. I think that comes from the from French, groupe modulaire. So that is the mapping class groups. And we are also going to consider a third class of groups, which is weakly amenable groups with a Cowling Haagerup constant 1. So I think you all know what this is. But yeah, if someone looks at this video afterwards, this is an approximation property for the group, for Neumann algebra of the group. So it's a generalization of amenability in the context of operator algebras and approximation properties. So for those classes of groups, we actually get this new weak form of the Haagerup property. So this is the theorem that I want to state. So if gamma is a group in these three classes, then there exists a measure space and a closed subspace of L1, such that gamma has a proper affine action on this subspace with a uniformly bounded linear part. So these classes of groups have this weaker form of the Haagerup property. And let me just mention that, so we already talked about hyperbolic groups. For mapping class groups, it's not known if they have the Haagerup property. So that's still an open problem. And for weakly amenable groups with Cowling Haagerup constant 1, this is usually referred to as the Cowling conjecture. So it's still not known if this property implies the Haagerup property. But for all the examples that we know of, they have the Haagerup property. But in general, it's still an open problem.
So Ignacio, so once again, let me interrupt. So for the mapping class groups, do we actually expect that they would have Haagerup property? Wouldn't they have property T in some cases?
Well, that's the thing. I think it's completely unknown.
Sure. Property. So yeah, I know it's not known, but I mean, I don't know what the expectation is somehow.
Yeah, then you would have to ask the experts.
Okay.
Yeah, but I don't know what people expect really.
Sure. Thanks.
So we have this, and this raises a lot of questions, but one in special, in particular, that can we say something about LP, right? Because we saw with the characterization of the Haagerup property that if we have an isometric action on L1 or even on a subspace of L1, we can extend that to all P, right? But if you look at the proof of those theorems, they use this isometric condition in a crucial way. And I would love to know if this result here can be extended for other values of P, if there is such a relation. I have no idea. And yeah, so I wanted to finish with that question, and I left here the main references. So the first one is like the Bible for the Haagerup property. Everything is there. No, not everything, but it's a very good book. On the second one, you have several extensions to actions on other Banach spaces, and also something about uniformly bounded representations. And the third one is my preprint with this last result that I stated. And with that, I'm done. Thank you.
Thank you very much, Ignacio.
Thank you.
Let's clap. Okay, I will stop recording.